Welcome. We're watching Nanotech today, communicating advances and trends in nanotechnology worldwide. I'm Dr. Argonne. We have a great program ahead of us with a renowned researcher in the field of concrete. Our guest is Professor Hamlin Jennings, who's a professor of civil and environmental engineering at Northwestern. Our topic today is the nanostructure of Portland cement, new approaches to studying an old material. We'll talk in sort of two parts in this half hour about cement and concrete in general, and then secondly about Professor Hamlin's specific research in this regard relating to calcium silicate hydrate, its properties and investigation. Welcome, Professor Hamlin. Pleasure to have you.
Thank you. Good to be here.
So, concrete and cement are extremely important subjects.
Yes.
And have implications in nanotechnology. Let's start out a little bit broadly about what concrete is, what cement is, and how, just inform us on what that is all about.
Okay, some of the language that we'll use in the next half hour is cement, which is, I'll come back to in just a minute.
Mm-hmm.
It's a gray powder, we're all fairly familiar with it. Water, which we're familiar with. Fine aggregate, sand,
mm-hmm.
and coarse aggregate, which is gravel, generally speaking. So we have cement, and you mix it with water, it turns into cement paste. It gains strength and hardness with the passage of time. And you add fine aggregate, or sand, and you have mortar.
Mm-hmm.
And coarse aggregate turns that into concrete.
Mm-hmm.
So concrete has been around in various forms for some time. I'll come back to that point. But the cement, which is the manufactured part, is made out of materials that are readily available all around the world. One of the main ingredients is limestone,
mm-hmm.
and the other main ingredient is clay. Limestone brings calcium to the mixture, and clay brings silica, which is the primary importance, but also alumina, which plays a secondary role in the hardening process. These ingredients are put into a kiln. The kiln is heated to extremely high temperature, and out of the other end comes a material that's generally about an inch in diameter. It's called clinker.
Mm-hmm.
And that is cement, which when ground up is either shipped in very large containers like trains or bagged into the 50 and 100-pound bags that we can buy at the hardware store.
Mm-hmm.
There's a lot of it used.
You say you're going to comment on the history of concrete. Obviously, just
well, in a bare bones kind of way, all the way back in early Egypt, the Egyptians had a lime mortar that they used. The problem with the very early versions was that if you put a lime mortar into an environment that's moist, like as a foundation for a house, it deteriorates. So the breakthrough that the Romans made was that they found a volcanic ash of pozzolana and when you mix lime mortar with pozzolana, it turned into a concrete which is very analogous to what we use today. It's waterproof, and the problem was that the fall of the Roman Empire, that technology went away.
The Dark Ages.
The Dark Ages.
Exactly.
The great structures, the Pantheon, for example, which has a roof that's made out of a extraordinarily sophisticated concrete. I saw a program on your competition PBS not long ago, which was the history of the Parthenon, the Pantheon, and how it was constructed. And they made the bold statement at the end, which was that if we used today the technology that was available then, we would not be able to build the Pantheon, because the gradation in the density, in the weight of the cement was very sophisticated, so that the roof was light and the side walls were dense and strong.
Got it.
That technology died away with the fall of the Roman Empire, and it wasn't until around the middle 1700s when it was reinvented in England. It derives its name, Portland cement, from a gray stone that was found on the Isle of Portland stoned, and they named it Portland cement as an artificial stone. So that was patented as under various names, artificial stone being one of them. And by and large, the chemistry and the character of modern Portland cement concrete is based on that 1750 type of thing.
Welcome back. You're watching Nanotech Today, communicating advances and trends in nanotechnology worldwide on Internet television. Our guest, Professor Hamlin Jennings of Northwestern. We're finishing up the half hour talking about calcium silicate hydrates, a major area of research interest. Tell us about that. First of all, what is the importance of that, and then let's dive into some pictures and nanotechnology.
Okay, so the glue that holds everything together in this whole big family of cements is calcium silicate hydrate. Calcium silicate hydrate is a incredibly difficult material to study. It's kind of like a jello.
We have the picture right now on the screen.
And so one of the objectives has been to sort of try to get down to see what this structure looks like at the nanoscale. Now, one of the important problems with this is that structure changes a lot if you dry it.
Sure.
So therefore, if you stick it into a normal electron microscope or into many, many different kinds of instruments, you're altering that structure.
So actually the process of looking at it is changing it.
It's changing it. So that's one of the reasons why we're still in the state of not fully understanding this much used material. So here we have two pictures, and one way to look at a material is that...
Bring that picture up again.
One way of looking at a material is to consider it a continuous material with a lot of holes in it.
That's the top
That's
picture.
kind of the top picture, and that's been the prevailing view for many years. The lower picture here is really saying, wait a second, this material could be maybe more accurately described as an assemblage of little tiny particles, 2 to 4 nanometers in diameter.
So the continuous versus discrete hypothesis.
So this is, well, we'll call it, I'll even use a different word, it will be continuous versus granular.
Granular, okay.
And that brings in a rapidly emerging field of granular mechanics, which means that we can if we can figure out what these particles are, how they're distributed, then the mechanics community can take that information, build multi-scale models, and actually predict properties at the meter scale.
So in terms of that interpretation, we have just a few seconds left. Is it the discrete granular model or the continuous model prevailing?
No question that it's the granular model that we're landing on. There's very hard evidence for that. Other groups at other universities, colleagues at MIT, for example, are now able to take that information, scale it up, and accurately predict the mechanical properties with the understanding that it's granular. Yes.
So it looks like nanotechnology is going to be really central to concrete and cement, this huge industry.
It absolutely is. One thing we didn't even have time to start is a lot of chemicals are added. Those chemicals go down and interact with the surface of these nanoparticles and change properties a great deal. So there's really a very bright future in the design of new materials.
So if I can make an analogy from my own field in life sciences, sort of drug development has been empirical, but also now more rational.
Yes.
So we're approaching the end of our half hour. Thank you very much, Professor Hamlin.
Thank you for having me.
You're watching Nanotech Today, communicating advances and trends in nanotechnology worldwide. I'm Dr. Argonne Advanced. Stay tuned until next week. We have some great shows coming up. Thank you.